Hi, everyone. Thank you, Anne, for recording the webinar. I suggest that we gently start, expecting that people will come in the coming minutes. So today for this webinar, Protect webinar, we have the chance to have ASIAQ mainly that will discuss their activities. Actually, it will be not one talk, but three talks. And the first one will be given by Kirsty Langley. Finally, Arno was not able to attend, if I understood well, and it will be followed by a talk from the government of Greenland, how they used tsunami models. And finally, this work was done in collaboration with BRGM, and Hideo Aiochi will speak a bit more about the methodology. So please, Kirsty, the floor is yours.
Okay, now I just have to get all the buttons right. Let's try and share the screen. We had a bit of trouble with this, but let's see. And I try to get it into... Which one are you seeing? Are you seeing the...
Just switch.
Yeah.
Perfect, thank you.
Yeah, okay, thank you very much. So I'm just going to give you a quick presentation then about ASIAQ and what we've been involved in within Protect. I apologize, this probably won't be quite as thorough as if Arno had done it. He was unfortunately unable to join us just in the last minute here. So I'll do my best to get us through his slides and elaborate where I can. So we sit and work in Nuuk, ASIAQ, the Greenland survey. And this first slide says a little bit about what ASIAQ is, who we are. It's actually a mythical figure who controls the winds and the weather, a Greenlandic mythical figure. So it's very appropriate for what we do here in ASIAQ. We're a company owned by the government of Greenland, but also undertake research and commercial activities as well. So it's yeah, a whole mixture of things that we do. Currently, we're approximately 20 employees, and this fluctuates depending on projects that we have going on. We're split into two groups. We have one group who specializes in surveying, mapping, and geophysical assessments for the commercial clients in the Greenlandic government. And this uses a lot of different geophysical tools, from UAV drones to bathymetry mapping, yeah, and other geophysical seismic methods, for example. And then the group that Arno and I sit in is hydrology, climate, and environment. And there the focus is on monitoring projects, hydrology and climate monitoring projects, but also other scientific and research projects such as Protect. Overarching, I think Arno's put it very nicely in these last two bullet points there, that we try to constrain and focus our activities on doing work that benefits the Greenlandic society. So this of course can be seen as very broad, but it also can be a little bit narrowed when we're looking at saying yes or no, or being involved in different things. And as more specifically, we would see ourselves as a company who's collecting, storing, analyzing, and disseminating data on the abiotic environment of Greenland. And I would say that this analyze part of it is also something that we like to highlight to potential partners, because it's not just that we do logistics and collect data. We are very interested in the processing and analysis and the findings of the data that we collect. One example one of the larger monitoring programs that we're involved in is the Greenland Ecosystem Monitoring Program. And this is one of the longer running ecosystem monitoring programs or monitoring programs in Greenland. It's funded by both Denmark and Greenland. It has 3 main sites, one here in Copperfjord, which is very close to Nuuk, one in ASIAQ, which a lot of people know as the Disco Island area, and one up in Zackenberg in a high Arctic location here. And the very nice thing about these projects is that very nice thing about the Greenland Ecosystem Monitoring Program is that it's built up through a number of sub-programs which each specialize in different parts of the ecosystem, but we're all under the same umbrella and the same funding, which means that we have a very detailed but also a very broad look at ecosystems within each of these 3 sites, as well as a few satellite sites as well. And all data within this is freely available online on the website for GEM. So then within Protect, ASIAQ was involved in Work Package 2 and Work Package 5. Starting on the Work Package 2, which was co-design and co-production of sea level projections and coastal climate services in case studies, of which Greenland was one of them. I think maybe this is the same for the other locations, but it got hit quite badly by COVID. All of the plans related to this work package, as I understand. And our original plan at ASIAQ was to serve as the connector between the Protect social scientists and local stakeholders and help organize stakeholder meetings in Greenland. And I would say that this did happen, but maybe a bit later than was originally anticipated. And we had a nice visit from Xenia in spring 2024, where she was able to both be in Nuuk and up in ASIAQ area and conduct the interviews with the local stakeholders. And as far as I understand it, this was successful, and Xenia was very happy with the trip here. So we're looking forward to then hearing more about that later on. I think probably at the next meeting, right, Xenia?
Yeah, at the last project meeting, I will present the results.
Super. And then, as Arno's put there on the final point there, localized sea level and ice melt projections are being created on the basis of the stakeholder needs, which is then feedback from what Xenia's been working on. Within Work Package 5, contribution of the Greenland ice sheet to sea level rise. So what we were, I guess, mostly able to help with from our expertise is the fact that we have the in situ climate data in areas that were particularly being targeted within the Protect project. So we have climate data in the Nuuk fjord system, and we also have had earlier remote sensing projects that were looking at ice marginal lakes and superglacial ice lakes, which could also feed in. And we've had close contact with Angelica from ARVI regarding this work, and she's actually here now on a visit, linked to actually both of these projects. So this has been a very fruitful collaboration that's come out from Protect, actually, is this close contact with ARVI and being able to overlap and work together with them. And then just finally, I'm not sure how I'm doing for time, but I'm already getting onto the final slide. To mention then, so we have both increased our work with ARVI, but also with DMI, and that's Arno sat there at the moment, and he's working with Ruth and the group at DMI, and this has also been a spin-off from, not a spin-off from, it is spin-off from Protect is our increased activities with DMI, but the work that he's doing there is directly related to DMI. And I'm going to have to just now read you the text that he's written for me, because this is very new stuff that he's on. He says, I'm visiting DMI right now. and we'll work on some of the simulations produced in the course of Protect that no one has had the time to look at yet, with a focus on precipitation. The left plot shows atmospheric gravity wave patterns in a regression analysis. The patterns are regression coefficients, while the right plot is a heat map of the frequency of occurrence of localized pressure minima, which may be related to the interaction of the circulation of the orography, which is particularly pronounced around Karat Fjord, the northernmost heat spot. I don't know if you can see my mouse, so it will be up here. So Arno is particularly interested in the atmospheric climatology, and has within ASIAQ, we've been working to try to better understand precipitation, which is a particularly difficult thing to measure, parameter to measure in situ, but it's also a particularly difficult thing to model. This modeling precipitation is often not very good, either not in the forecast, but that's another thing. So Arno's been putting a lot of time into thinking and looking at precipitation now in the past months, and this work going on with DMI will help to then put together again this in situ work together with DMI's larger climate-based database that they have, and the larger computing power that they have. And we'll link it up then to Protect, because it will be using, as he says there, the simulations that have been produced throughout Protect. So thank you very much.
Thanks a lot for this nice story of the activities, and very happy to see that Protect helped to tie the link with DMI and AVI, but also initiate new collaboration through BRGM. I don't know if there is a question, or we can keep all the questions for the end, and then in that case we move to Eva Mätzler and Jonas Petersen. So please share your slide. We are listening to you. Thank you.
Hello, we'll try and share slides now. Is it working?
It's perfect.
Perfect. Yes, we're with the Department of Geology under the Ministry of Business, Trade, Mineral Resources, Justice, and Gender Equality. And yeah, this changes a lot with politics, but we're 12 people in the Department of Geology, and the department works with mineral exploration and marketing, and also carbon capture and storage, and landslide monitoring. And landslide monitoring, that's the three of us: Eva Mätzler, Jonas Petersen, and me, Alexander Gamble. We started the landslide group in 2021, and got our first monitoring systems in 2022 and 2023. A lot of our work is maintenance and daily monitoring using these systems and sensors on the unstable slopes. We also do field surveys and citizen meetings, and then also monthly situation assessments. And a large part of our work is the continuous updating of the landslide scenarios, which is based on our field survey data, and which leads to volumes and sliding characteristics of the unstable slopes, which are then fed into tsunami models, which we use to create run-up maps. And now Jonas and Eva will tell a bit more about how we create these tsunami models and run-up maps, and who we work together with.
Okay, thank you. I'm Jonas. I would like to present the next 5 slides. And yes, modeling is the one of the things that we also are doing in collaboration with our external collaborators. Yes, our main interest is to see what could happen in the future, and the models would help us telling us what could happen in the future. That's why we have developed a three-phased the workflow. First, with the models of the dynamics of the landslides that could trigger tsunami. Based on our field survey data and the monitoring data. Those should give basis of the rapid mass movement simulations, and the scenarios are defined by the process understanding in the field, and then all those could be put into the initial conditions for modeling the tsunami and the impacts for the different sites, which I will briefly discuss in the next slides. Yeah, the understanding what is happening of processes in the mountain slopes is a key to the basis of models that should be created, and we do as Alexander have mentioned, field surveys, and out of that, we've been able to define different scenarios with different probabilities. Some are the more probable than other scenarios, and we use 50 years of reference period for the predictions. And the initial conditions should be based on how much of discharge the slope failure could trigger into the seas. We do model the landslide tsunami generation coupling with this the landslide models done by external collaborators as well. And then all those the landslide scenario for each landslide scenarios there has been run numeric nonlinear the tsunami models for the entire basin of the Umanak Fjord system. You can see you can say about the arrival times, front times for the waves, and the inundation heights based on those tsunami models. And this is a hindcast of 2017, the landslide triggered tsunami that we see the visualization as in the model here. All right, all those the tsunami models, the model data results are put into to tell how the different settlements and the populated areas could be affected with regard to the time of the wave. The time of arrival of the waves, also with the coupled with the different the scenarios with different probabilities. We do also try to tell in those the models the intensity of the impact of the tsunamis. In this example, colored given by color coding. and finally we present them to for each living populated area as run-up maps. Yeah, Eva will take over now.
Yeah, and all this work, we are only 3 people here in our group, so we have a lot of collaborators, both in industry, with other authorities and research. We also work, among others, with ASIAQ on with a climate station that in one of our monitoring sites. So, and with this first slide, we just want to invite you. We are always open and happy to hear how we can work with different collaborators and also scientists to help us to get some better risk maps or tsunami models. So I make just 2 slides to show in 2 examples where we still need some more information and where we see there could be a potential for scientific collaboration. One of them is to better understand the effect of sea ice on the tsunami evolution. And as far as we know, there is at the moment no tsunami model that includes sea ice. So we can understand how it affects the generation, the propagation, and also the run-up with different types of sea ice. And this is a question we regularly get from local population. They are very interested in and have also quite a lot of local knowledge on that matter. So we think it has an impact. It might dissipate the energy, and also it would be really interesting to understand how it works with different sea ice conditions. And so it might have an impact on the seasonal variation of the sea ice and our tsunami hazard assessment. And another thing we, in our case, is we are mainly interested in the big rock avalanche that happened, and they are, or it could also be a big ice avalanche or some other things, but the main common is they might have some cascading events, and how we could integrate different models more smoothly to integrate, for example, this rapid mass movement simulation into the tsunami model that can help us to have a bit more smooth workflows on that, or interaction between, because it's always different science, different disciplinary, and it could be nice for us to get there a bit more smooth interaction and have a look into these cascading events also in modeling. Yeah, I think that is what we have from our side. So you are also afterwards very welcome to contact us. And we have one homepage that is at the moment still very few information, but at least we do each month's risk assessment on our monitored site that you can have a look.
Thank you. I have a series of questions, but maybe they are more pertinent after Hideo talk, which is presumably is very linked to that one. So I suggest that we move forward and keep all our questions for the end of the webinar. So please, Hideo.
Okay. Thank you. Okay, so hi everybody. So I'm Hideo Aiochi, so from BRGM, and this is the collaboration with Masumi Yamada and Chun Chong Ho, working at Kyoto University. It was just an occasion that because they were interested in Greenland. And we, Yamada-san and myself, are rather on the geophysicists. So seismologists. So we are interested in how to detect the tsunami or some events from seismograms. That's what we are interested in. So my talk is a little bit different, but The topic, the focus is how seismograms contribute to detect the tsunami generation and passage. And here, of course, so everybody now, I think you all know what happened in the past. So there was a tsunami at the center, the west center of Greenland in 2017. And of course, that the village was devastated. And so there's no tidal measurements, but we have one seismograms near the village. And it recorded very well the landsliding and the tsunami passages. Okay. Okay. So there were in the literature. So there are some people already worked on this earthquake. So just after one year later. So a group already worked on the tsunami generation and tsunami propagation, and then explaining what happened in the seismograms. So there was the first attempt. So I don't. So the time is very short. So I don't explain in the detail, but. Another example is from a French group, and they simulated the tsunami simulation. Rather, they support a very simple tsunami generation process, but they simulated the tsunami and they estimated the tsunami height in front of the village is about 1 meter or something like that, and compare with seismographs. So what we are doing, so the three researchers, so that one person working on the analysis on the seismograms, and one person is working on the landsliding and the generation of tsunami, and then the propagation. Well, of course, it is a very simple model. And then another person, so myself, in fact, I am calculating the elastic vibration due to the tsunami generation and propagation. So here, this is a station. So I think here it is from the IRIS, or International Seismological Network. So here this is a village, and the one station is around here. So we don't know exact distance, but we estimated about some 100 meters. And of course, the seismograms, what is important, so seismograms detect the ground motions at different frequencies. So here, the left column, it is raw data. That's what we observe directly on the sensors. And here, this is the velocity, and we interrogate once the velocity. So, and different frequency range. For example, here, this is, oh, I don't see my, yeah, here, this is a 10 to 15 seconds. And here, this is a more longer period, as you see. So what we can observe is completely different. That means that the onset of the seismograms corresponding to the tsunami generation, landsliding and tsunami generation, it is a high frequency. But later, so we observed a very low frequency, so very long period oscillation. It is correspond to the tsunami propagation. So it doesn't go to next page immediately. Oops. Yes. Okay. So here, this is a classical, a kind of a classical seismic wave analysis. So we know where is the source, the earthquake source, the origin of the oscillation. So we can obtain which kind of the source applied on the ground surface to generate the seismic waves. So it is quite very well fit the seismic waves in the regional scale. Then, of course, but For example, if we focus on the one near the closer station, so 30 kilometers away, it does not fit very well because we don't know the detail of the process. Of course, so the faraway solution is good, but we cannot know the detail of the process. But it is a kind of a limit of the seismology wall. Kind of the limit of our knowledge of the structure and some complex processes. Then, so if we know the seismic source, that means that we know which kind of the force it applied. Oh, applied. Oh, my video is over. Okay. So, of course, after some other information like image INSA analysis and some other literature, so we can estimate the volume of the landsliding. So here, Paris literature that says that about 50 cubic meter, and we tested it twice. Well, you can see that now, in fact, it does not change a lot, the estimation. Here, this is the first, the wave estimation. It's about a 30 kilometer away, that the position of the village. But even if we multiply twice the volume, so it does not change. So it is a kind of limited by the geometry and some other factors. So here, you can see that the landslide area is like that, and well, of course, it is a simple assumption. So the angle is just one parameter. But while we let the landsliding into the sea, then this it generates the tsunami propagation. So and for the tsunami propagation, of course, as everybody do, the bathymetry is very important. And yeah, it does not move. It's just a snapshot, static snapshot. So in fact, it's very high. I think it is at the origin of tsunami generation. The height of tsunami will arrive at more than 50 meters. I don't know if it is reasonable for those who are working in real, but numerically it arrives more than 50 meters or something, and then propagates, and so 30 kilometers away at a village it becomes about 1 meter at maximum, like that. And we don't have a run-up here. It's just so it is, the boundary is fixed by the coastline, and then of course at the outside it is, of course, that is a boundary condition, of course. And so so that's what I say, that here this is at the position of the village. So we have a kind of the 1 meter tsunami height at maximum, and we change the landslide volume, but it is somehow saturated, means that even if we change it twice, so it does not change a lot of the tsunami height at this distance. Then, so we're interested in how the elastic medium. So, of course, that the idea, it is essential to have tidal gauge, but it's not always the case. And if we have seismometers near the coastline, we can observe this tsunami movement. So that's what we are testing. So it's just simple example, synthetic cases. So the tsunami waves are kind of the image moving from right to the left. And of course, that it is elasticity problem. So we can use static problem. Well, static problem, that means that tsunami wave is enough slow comparing to the seismic waves. In that case, we can use a static solution, but we also tried finite difference simulations. That means that elastodynamic simulation. In that case, we can consider the surface wave, even if its tsunami wave is much longer wavelengths. In our tests, we find that the surface wave effects, that means that it is oscillating, and it kind of the dynamic effect becomes more important. And here, this is the real case of the 2017 tsunami case. And well, a lot of the fears, but here this it is a seismological description, but we can see, for example, PGDZ, it is a maximum value of ground displacement. So, and of course, a small dot is under the sea, so we don't count. But it is not so good resolution, means that the receiver position we put, it's not so good resolution, but we can see that it arrives somehow that 1 meter near the coastline like that. And here, this is how it is attenuated. Of course, that tsunami height is much larger at the source point, the origin of the tsunami generation point. So it is very high in the estimation of the ground motion. And here, this is a time series. So in the dynamic finite difference method, we can have a kind of millimeter order of displacement fields. So I summarize here. So from this exercise, we can monitor the coastal risk, means that tsunami wave passing propagation from the seismographs. And the technical barriers towards a real-time application, of course, are distinguished, of course, as well. Posteriorly, we can always work, but if we like to use for a kind of monitoring system, so distinguish a landslide event from earthquake, it's not so immediate. We need kind of expert's opinion. But now, so recently, since a few years, so artificial intelligence is very, very common. It's not perfect yet. The community is trying. And ground displacement due to the tsunami is limited. That means that we only have one point in this case. Of course, it can detect that tsunami wave propagation, but of course, if we like to monitor, so we need to have a multiple points. So how can we develop cheaply the network? So well, of course, it is very expensive, but the community, so optical fiber network is. Optical fiber itself, it's not so expensive. Of course, it is the emitter and capture is very expensive, but yeah, it is a one option. And of course, that well, one event is very difficult, but some literature says that for concerning about landslides, so there might be some seismic precursors. So that's a topic of research, how to detect. It's related to the first question, but how to detect such precursors. So so we worked on the 2070s events, but of course that now, so there are I don't say more and more events, but in the community we know that there's some other events. So the people are working in especially that there was a big landsliding last year, I think. So I think that people are more and more cautious about not monitoring, not only the monitoring, but understanding this phenomenon. Okay, thank you very much.
Thanks a lot for all these talks.